In this lecture, we are going to start the design of helical tension spring. So the helical tension springs are used to carry the tensile loads, and the procedure for helical tension spring is almost like the helical compression spring, except the calculation of total number of turns and calculation of free length. So the remaining procedures are same. So the first step is calculation of dimensions. So in the problem, they will specify the shear stress of the material and the spring index and load value. So by substituting the value of tau ks p c, we can calculate the diameter of the wire, and we know that the spring index c is the ratio between coil diameter and wire diameter. So by substituting the value of d in the c equation, we can calculate the capital D. So after calculating the diameter of the spring, then the second step is calculation of number of turns. So this equation is also there in the data book page number 7.100. Del is equal to 8pc cubed n divided by gd. Here del is the deflection, p is the load, c is spring index, n is number of turns, g is modulus of rigidity, and d is the coil diameter, the wire diameter. So by substituting the known values, we can calculate the unknown value, that is the number of turns. Then after calculating the number of turns, we have to calculate the total number of turns. So for all the helical tension springs, the end conditions are same. So the end is a curved like structure. So the capital N is equal to n plus 1. So it is common for all helical tension springs. Then calculation of free length, LF is equal to nd plus n minus 1. So here n is the small n, that is total number of active coils. So n into d plus n minus 1. Okay, so this is for the clearance. Then finally the calculation of pitch, P is equal to LF divided by n minus 1. So after calculating all the dimensions, we can write everything as a resultant dimensions. Fine. So this is the drawing for helical tension spring. So this is the coil diameter and small d is the wire diameter, di is inner diameter and do is outer diameter. The distance between adjacent coils is called as pitch, and the length of the spring at the elongated state is called as free length. So the first problem, design a helical spring for a spring-loaded safety valve, ram's bottom safety valve. So remember that the technical term ram's bottom safety valve. So this is the ram's bottom safety valve. So this is the structure, and here in the ram's bottom safety valve, that helical tension spring is used. Okay. So whenever in the problem, if you see the word ram's bottom safety valve, then we have to select the helical tension spring, not the helical compression spring, because there will be no difference in the problem. Okay. So only thing for ram's bottom safety valve, we have to use the helical tension spring. So the diameter of the valve seat is 65 mm. The operating pressure is 0.7 Newton per mm square. So here we have two pressure values. The first one is operating pressure, that is P1. So just like the pressure relief valve design. Then maximum pressure when the valve blows off freely. Okay. So once after reaching the 0.7 Newton per mm square, what will happen is the valve starts to blow off. Okay. So after reaching a high pressure of 0.75, the valve is completely opened. Okay, so the valve is completely open. Remember that the valve starts to open at a pressure of P1 and it is completely open at P2. Okay, the maximum lift of the valve when the pressure rises from 0.7 to 0.75 Newton per mm square is 3.5 mm. So this lift from 0.7 to 0.75 is 3.5 mm. Okay, so the maximum allowable stress is equal to 550 megapascal, and the modulus of rigidity is equal to 84 kilonewton per mm square, that is 84 into 10 power 3 Newton per mm square. Then the spring index is given as 6. Okay, so in the problem, the P1 value and P2 values are given. So by using the P1 value and the diameter of the valve dV value, we can calculate the load 1 and load 2. And this 3.5 mm is actually the lift, that is the deflection from P1 to P2. So it is del. So 3.5 is equal to del. So we have already solved this kind of problems earlier. So you know what is the meaning for del, that is the deflection from P1 to P2. Okay. So in the case of helical compression spring, it is compression, and in the case of helical tension spring, here it is the elongation. Okay. So del is equal to 3.5 mm. It is the elongation of the spring. So we'll calculate the P1 and P2 first. So P1 is equal to pi by 4 dV square into small p1. Substitute the value of dV and P, so that the maximum, the minimum pressure is, minimum load is 2322.8 Newton. Then for maximum load, substitute the maximum pressure value. It is 2488.7 Newton. So after calculating the P1 and P2 value, we can start the design procedure. So the first step is calculation of dimensions. So tau is equal to Ks 8P2. We know that for calculating the shear stress, we have to use the maximum P value. Okay. So if there is only one P value in the problem, then there is no confusion about that. But when you have two load values, that is P2 and P1, you have to be very careful. And for calculating the shear stress, you have to select the maximum load. Okay. So it is Ks 8P2 C divided by pi d square. So tau value is given in the problem, it is 550. You can substitute that. Then C is given as 6. So the equation for Ks is 4C minus 1 by 4C minus 4 plus 0.615 divided by C. Substitute the value of C in this equation so that you will get Ks is equal to 1.25. So now you can substitute the value of Ks here and C and the maximum load. So by solving this equation, you will get the diameter of the spring, that is wire diameter, as 9.3 mm. So after calculating the wire diameter, you can substitute the wire diameter in the C equation, that is C is equal to capital D by small d, so that you will get the coil diameter D is equal to 55.8 mm. The second step is calculation of number of turns. Use the equation del is equal to 8p c cube n divided by gd. So del, it is directly given, it is 3.5 mm, and P. So we know that we have two load values, one is P2 and the another one is P1. So the valve starts to open at P1 and it is completely open at P2. So this distance is deflection del. So when you are substituting the del in the number of turns equation, you have to substitute the P value, that is load range for this amount of deflection. Okay, so what is the load range for del deflection? And we know that P is equal to P2 minus P1. So it's very important. Okay, so P2 minus P1, P2 is given, P1 is given. So P2 minus P1 is 165.9 Newton. So substitute everything in this equation and calculate the n value. N is equal to 10 turns. So n, small n is actually the number of active coils. Then the total number of turns for a helical tension spring is capital N is equal to n plus 1. Capital N is total number of turns including active and inactive turns. Okay, so the difference between active and inactive turns is the active turns will carry the load and the inactive turns will not carry the load. Okay, so in general the inactive turns are at the end side. So here the active turns is 10, so it is 10 plus 1, that is equal to 11. Then the fourth step is calculation of free length, and the free length for a helical tension spring is LF is equal to ND plus N minus 1. So we have all the values, substitute it, you will get 102 mm. Then pitch, P is equal to LF divided by N minus 1, so it is 10.2 mm. So the last step is resulting dimension, write all the calculated dimensions in the final step. Okay, so this is the design procedure for helical tension spring. So there are two differences. One is the total number of turns and the another one is calculation of free length. According to this problem, remember that In ram's bottom safety valve, helical tension spring will be used. Okay, it's not a helical compression spring, so be clear about it, because in the problem they haven't specified anything about helical tension spring or helical compression spring. Okay, so the only keyword is ram's bottom safety valve. So the tutorial problem, a spring for a spring balance is to elongate 100 mm. Okay, so here the spring is used to elongate. Elongate means it is providing some, it is capable of carrying tensile load. Okay, so the gel is 100 mm and the meaning for elongation is here the spring is a helical tension spring. Okay, so it's not compression spring, because the compression spring will not elongate. The compression spring will compress, the tension spring will be elongating. Okay, so here the spring is a helical tension spring when subjected to a load of 20 kgf. So it is actually given in kgf. You can convert it into Newton by multiplying 9.81. Assume that the mean diameter of the coil is to be 6 times the diameter of the wire. So the meaning is capital D is equal to 6 times the wire diameter. So C is equal to D, because D by D you will get 6. The maximum stress to be induced is limited to 40 kgf per mm square. So tau is equal to 40 into 9.81 Newton per mm square. Design the spring. Take G is equal to 0.8 into 10 power 4 kgf per mm square. So here also multiply 9.81 to convert into Newton per mm square. Okay, so convert all the kgf values into Newton, but remember that here only one load is given and only one deflection is given. So we don't need to calculate the pressure differences, del max, P1, P2 and all those things. So directly you can take the P value, you can take the del value and you can start the design procedure.